This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on Introduction to Radians. So what can we talk about here? What's our idea? One circle has 360 degrees, so that's something most students are well aware of. But one circle also has 2 pi radians. Now where does that come from? Where does that idea come from? So again, we call these things radians. But the reality is this: if I have a unit circle, a circle with radius 1, the circumference is 2 pi times the radius. The circumference of a unit circle is 2 pi. So we think of the central angle of the circle matching how many degrees of arc we have. So that's in essence where the radians come from. And in calculus, radians are much preferred. So it is advantageous for students to become very comfortable with this unit of measure. So let's take a look at how we're going to go ahead and do our conversions. So indeed, we know that 2 pi radians is the same thing as 360 degrees. Good to remember that. But we could also divide that by 2, in which case we would say pi radians is 180 degrees. And that usually makes things just a little bit easier to work with. So if I'm converting between radians and degrees, I typically use the fact that pi radians is 180 degrees. So here's one of our questions. We're going to say convert 60 degrees to radians. Now how are we going to do that? We're going to multiply 60 degrees by a fraction. I want degrees to cancel, so degrees will be on the bottom and radians will be on the top. But that fraction has to be 1, otherwise we change the meaning of the number. So if I want degrees on the bottom, that will be what, 180 degrees on the bottom. Pi radians on the top, but that fraction is really just 1 because pi radians and 180 degrees are the same. So here's our process of converting. What are we going to start with? We're starting with 60 degrees. And we're going to multiply that by what? 60 degrees over 1, so you can see it as a fraction. We want degrees on the bottom and radians on the top. So pi radians is the same as how many degrees? Is the same as 180 degrees. And again, I want you to recognize this fraction is a funny name for 1. 60 degrees times 1 is still 60 degrees. We just may change its name. Degrees will cancel, so we'll have 60 pi radians over 180, which is going to reduce to what? We'll take a look at that here in a minute. So we have 60 pi over 180 radians. To reduce that fraction, divide the top and bottom by 60. 60 pi divided by 60 is just pi. 180 divided by 60 is 3. And what we have here is we have pi over 3 radians. You probably want to memorize that 60 degrees is pi over 3. 30 degrees is pi over 6. 90 degrees is pi over 2. 45 degrees is pi over 4. You really want to become comfortable with those because we use them so often. Now let's go ahead and convert the other way. If I give you degrees, how do we convert back to radians? What will our process be? So this time I'm starting with how much? I am starting with 3 pi over 4 radians. Same process. Multiply the top and bottom by a fraction that is essentially 1, and we want to convert radians to degrees. So when I multiply by that fraction, I'm going to need degrees on top and radians on the bottom. Degrees on top, 180 degrees. Radians on the bottom, pi radians. That will enable radians to cancel. Let's see what that looks like. 3 pi over 4 radians times a fraction. We want radians on the bottom and degrees on top. What do we know? What's our relationship here? We know that 180 degrees is the same as pi radians. So when we need things to cancel, radians cancels radians, pi cancels pi. What I'm left with is 3 times 180 over 4 degrees. Let's make sure we're clear where that's coming from. Radians gone, degrees left, pi's gone, 3 times 180 over 4. Sensible way to do that. How many times does 4 go into 180? Let's see. 4 goes into 18 4 times with 2 left over. 425 times. 3 times 45 degrees. So what will that be? Reducing that fraction. 3 times 45 degrees, which I believe is 100 and 35 degrees, which puts us in quadrant number 2. So we can see that 3 pi over 4 is equivalent to 135 degrees in quadrant 2. So our next question is to find the arc length of a sector where theta is 2 pi over 3 and r is 10 centimeters. If we're thinking of this, we want to think of a piece of pizza, a circular pizza cut in sectors. So the central angle is 2 pi over 3. Remember that pi radians is 180 degrees. So 2 times 180, 360 divided by 3. That's a very, very large piece of pizza. That's 120 degrees. So you can see that this sector is 1/3 of the entire pizza. So the arc length will be 1/3 of the entire circumference. We know the circumference of the entire circle is 2 pi times r. So in this case, the circumference is 2 pi times 10 centimeters, or 20 pi centimeters. But we don't have the entire circle, we have a fraction of the circle. So I use S for arc length of a sector is going to be that fraction of the circle. 2 pi over 3 is our portion divided by the entire circle that has how many radians? 2 pi radians. If we're to reduce that fraction, you'll see that it's 1/3. So that fraction times the entire circumference is my arc length. So you'll notice how I'm going to do this. I want to generalize the rule for the arc length. 1/3 here times 20 pi centimeters gives me 20 pi altogether. Now, exactly what does that mean? 20 pi over 3 centimeters. 1/3 is my fraction of the entire circle. 1/3 of the entire circumference. They'll give me the arc length, the distance from there to there. Of course, 120 degrees, a little bit more than that. So our arc length is 20 pi over 3 centimeters. But we can get a rule here for this. What can we say? In general, it's going to be the fraction of the circle, theta divided by 2 pi. So theta divided by 2 pi tells me how much of the circle I have. If I multiply that by the entire circumference, I will get my arc length. The entire circumference is 2 pi times r. So if I have theta divided by 2 pi times 2 pi times r, all that's left is r theta. But you need to know that theta is measured what? Theta is measured in radians. If we're going to use this technique, r theta, for the arc length of a sector, we must have it measured in radians. So we can just take a quick look at our example. What did we have? Our r was 10 centimeters and our theta was 2 pi over 3. So if we make that substitution, 10 centimeters times 2 pi over 3, it's going to give us how much? It's going to give us 20 pi over 3 centimeters, which exactly agrees with what we said earlier. Now, that is the arc length of a sector. We can also look at the area of a sector. So let's discuss this question. We want to find the area of the sector with a central angle of pi over 4 and a radius of 6 centimeters. So pi over 4, 45 degrees, 6 centimeters all the way around. Well, if we want the area, we'll find the area of the entire circle. The area of the entire circle is pi times the radius squared. Area of the circle is going to be pi times 6 centimeters squared, 36 pi square centimeters. But this sector is a fraction of the circle. What fraction? Maybe it's obvious, right? It's 1/8. 45 degrees, right? 2 of them make 90. 8 of them make an entire pizza. So we have 1/8 of the entire circle. So you could jump right there. But I want to develop the formula here. So we're going to go with the fraction. We have pi over 4 radians out of 2 pi total times pi r squared. So you'll notice that these pi's would cancel. So I get 1/2 times pi over 4 times r squared. This is getting us ready for our formula, right? 1/2 times pi over 4 times 6 centimeters quantity squared. So pi over 8 times 36 square centimeters. If you divide top and bottom by 4, 36 divided by 4 is 9, 8 divided by 4 is 2. 9 pi over 2 square centimeters. Fine. That's relatively easy. But in general, you can see how this formula is going to be developed. If I want the area of the sector, how many square centimeters of pizza do I have? My angle is theta divided by 2 pi total times pi r squared. So again, what do we have here? The area of the sector, theta divided by 2 pi, that's your fraction, times pi r squared, that's the entire circle. Pi's cancel, so you just get 1/2 r squared times theta. That'll give us the area of a sector if it is measured in radians.